We're looking at the first derivative test here, which is a way of knowing the shape and behavior of a function and letting that tell us something about where we expect to find local extrema, local minima, local maxima. So jumping right into that. The first derivative test involves checking the sign or the plus or minus of a derivative if it changes on either side of the critical point. And if so, there is a local extrema, or extremum, if we want to be proper with our Latin, I believe. So if the derivative goes from positive to negative, we know that looks something like this. So it was increasing and now it's decreasing, so that will be a local max. If it goes from negative to positive, we know that looks something like this, going down then coming up, so that's a local min. And if it doesn't change, then it is neither a local max or a local min. And that's because it'll do something like either, let me take a second to think through what that's going to look like. It's going to go like this or like this. So it temporarily goes flat in the middle and then continues increasing, or it temporarily goes flat in the middle and continues decreasing. So our first example, find the local extrema for the function f of x is equal to x cubed minus 3x squared minus 9x minus 1. So first we need to find the critical points by finding the derivative. 3x squared minus 6x minus 9. Set that equal to 0, and if you solve that, you find that f prime of x can also be rewritten as 3 times x minus 3 times x plus 1. I'd already factored that before, so you can pause to double check that if you want. This means that x equals 3 and x equals negative 1 are our critical points. These are the places that might be local extrema. So we need to pick points on either side. So f of negative 2 is something that's going to be to the left of negative 1. And that's going to have a positive value. So you can just plug that in real quick and we see 2 squared is going to be 4, so I have 12 minus 9. I don't think that's right. Oh, sorry. I should be checking the derivative here, negative 2. Yeah. It'll be easier to check on this function. I did that too quickly in my head. Yeah, it was 12 plus 12 minus 9. But we can also check it easily, nice and easily here. Negative 2 in this first term is going to give us a negative value times another negative value times a positive value means overall it's going to be positive. F of 0 is going to be between negative 1 and 3. And plugging that in, I get a negative times a positive, so that's going to be negative. And f of, let's just say 4, because that's going to be on the other side, I get a positive, and a positive, so this is positive. So negative 1 on the left side, I've got positive. On the right side, I've got negative. That looks like this. So there is a local max at x equals negative 1. For 3, I go from negative to positive, so that looks like this. So there's a local min at x equals 3. Now, you can actually plug in the numbers and get the actual value out, but this ability to look at it quickly and just figure out from, say, your factored thing or from here, positive and negative values is something that's really nice to be able to go a bit quicker. So we're going to look at a slightly more complex answer now, which is the function f of x is equal to 5x to the 1/3 minus x to the 5/3. And this, if we find our derivative, is equal to 5/3 x to the negative 2/3 minus 5/3 x to the negative, no, not negative, to the 2/3. Okay, so this is something that you'll have to use a calculator for or graph. So I'm going to pull up my graphing here and just type that in. So I'm pulling this up to the side. You can do it yourself as well. So 0 is equal to 5/3. Y is equal to, we'll find our zeros. Y is equal to 5/3 x to the negative 2/3 minus 5/3 x to the positive 2/3. And this will give you -1 and 0, or -1 and +1 as your critical points. Which I guess actually we could see that kind of by inspection, that these are the same, just with, these will be the same when x is 1. So x equals ±1 are our critical points. And now we can pick and plug in values. So f of a number less than -1, let's say -2, is going to go in here, and if we're dividing by -2, that's going to make this one bigger. So it's going to be, sorry, no, it's going to make this one bigger, so that's going to be negative. F of 0 is not going to work because I can't plug it in here. So I'm just going to actually look at my graph of this and see that f of -0.5 is going to be positive. And then f of 2 is again going to be negative because of the same logic that we used before. So you're from negative to positive to negative, and that means that there is a local min at x equals -1. There's a local max at x equals 1, because we go from positive back down to negative. And actually we should check the 0, because that is also a critical point where the function is undefined, again because you can't have that here. But we'll see that if you also plug in f of 0.5, that also is positive. And so neither occur at 0. And I'm just realizing that because I was looking at my graph here. If you want to talk about kind of interpreting it from the graph in class, just graph this out and we can talk about it.